Good afternoon, everybody, and welcome to today's Adams training for the Cars4mars competition. I am Paul Nadir, the Managing Director of Simtech Engineering, and I've been an Adams user myself for the past 25 years. The main aim of today's training is to make you aware of this technology that you have available to you and how you can benefit to use it for this competition. Now, just a brief background of our company. We've been in business since 1995 and started to represent MSC Africa and other software vendors in South Africa and, well, the whole of Africa and UAE since 1995. We had a few name changes along the way, and today we are called Simtech Engineering. On the screen, you see our technical team, and we have represented various engineering technology companies across Africa and the UAE. We specialize in engineering analysis and simulation technology, and we cover a complete range of tools that you need when you develop any physical product. However, we help our customers to design, analyze, and even manufacture their products virtually. In other words, on computer before they build anything. This is to make sure that it will work when they build that first prototype they will use for testing, so that it will pass all the requirements and be ready for mass production. The value of simulation is that you can save a lot of time and money by not having to manufacture and test. You can literally design, analyze, test, and start with your manufacturing. We sell this technology in Africa, and we provide the training as well as the technical support for it, as well as we offer our customers also consulting services should they need it. We are really passionate about technology and love helping people to make their lives easier and their companies more profitable. Now the question is, what is Adams and what is it used for? So Adams is a system dynamic simulation package, meaning that you can represent any system of components that move and analyze how they will behave in the real world with contact, with friction, with play, and even flexibility. And here's a few examples. This example shows how all the major motor manufacturers in the world use Adams to test and improve their vehicles' dynamic stability control systems under different conditions. Tests like these can become quite expensive if you have engineering teams doing all these works, setting up the tests, instrumenting the vehicles. And the other thing about physical tests is that it's hardly ever possible to actually repeat the exact same test under the exact same conditions. While on a computer, you can have the exact same conditions and only change one thing and immediately see precisely what the effect of the change is on the design that you have. And this is another example of where Adams is used to design massive machines where you can't afford to build prototypes and where the first one you manufacture must actually be sold. And then you obviously need to make sure or know that it works. This is an example of a small tracked vehicle with flexible tracks. So that's another example of how Adams can be used. Just get back to this one that I actually wanted to show. So this is an example of a quad bike hitting a ramp. Now I'm pretty sure if you're the guy or the girl on the quad bike, you would want to make sure or want to know that it will actually stay intact and not break. But if you're the designer, it's very difficult to know what those forces will be that you will typically encounter when you do a stunt like that. So this is where Adams comes in. You can now literally simulate the event and measure the forces on each and every component at each and every connection. There's a close-up video of the exact same quad bike focusing on the lower control arm, and we can see the forces when it hits the bump, when it lands, and when it rectifies itself afterwards. And this is typically what we do with simulation. Now, the cool thing about having those forces is that we can use another technology called generative design, as in this example, where we now use those forces and let the software design a structure for us. And this structure is then not only strong enough to survive those events, but also the lightest possible. In that way, we make sure that we have less mass to carry around, makes our sports cars faster, it makes our aircrafts fly longer and use less fuel. Now, it's important that we just revisit a few theoretical terms that you should have learned in school already, or if not, you're still going to learn. If you're at university, you should definitely know this by heart. And that is the relationship between force and torque. So a force is literally a load or a force that we typically apply in a specific direction, while a torque is when we use that same force and we apply it over a certain distance around a specific point. So if you have a motor and you have the axle of the motor and that axle applies a torque, you could easily measure the torque by applying an arm to that axle and measure the force that is acting at a specific distance. So for instance, if you have a small little electric motor like this available at home lying around and you don't know what the torque characteristics of this electric motor is, you could easily attach a long arm to it, apply the voltage to it, make sure that you hold it quite securely, and then measure the kilograms or grams on a scale that it can actually apply to it. And using the relationship between mass and gravity, you can calculate what the force is. And then if you know what that distance is, that force was applied over, you can measure what the torque was that this motor can apply. Now, of course, you wouldn't want to do this for a large electric motor. You'll definitely get injured. So be very careful with that. But that is a simple way to determine, what the torque characteristics is of these small electric vehicles that you typically find in hair dryers and toys, etc. So once you have that value, that is essentially the single location, and let me just put my laser on. That would be this single location on the graph over here that you've measured. So that is the torque at stall or startup. And an electric motor has typically the characteristics that for a range of speed, it maintains the same torque, and then after a certain point, it would start reducing the available torque until it gets to a zero, whereas the power that it uses will increase to a certain point and then drop again. Now, this is just an example for a typical electric motor. Different electric motors have different characteristics, so it's important that you understand which electric motor you sit with, and if you can obtain this graph, that will be extremely valuable to you, because as you can see, the faster the motor rotates, the lower the torque is that it can supply, and those are the characteristics that you need in an atom simulation if you want to evaluate correctly how this system will behave. Now meet Marcy. Marcy is the rover model that you will see on the trophies that we have sponsored for the Cars4mars competition. And in this atom simulation, we took Marcy for a spin on Mars to see if it can navigate over this really extreme and rough terrain. And because Marcy weighs 1.5 tons, at least in this simulation, not on the actual trophy, it is quite important to know how large the electric motor should be to have this rover actually navigate this difficult terrain. And that is what we are measuring at the bottom left corner over here. So as you can see, Marcy struggles to get a grip on this higher slope. We can actually see what the torque is on the different wheels. And then as it goes downhill, because we've defined the motion, you will actually see that it requires torque in the opposite or negative direction. But we will talk a little bit more about this later. In this view over here, you get a bird's eye view of how Marcy is moving over the difficult terrain. The Adams model that was provided with the software and the training material includes this terrain. Now, just a word of caution, this file is quite large, so you might find that anything you do or simulations that you attempt in it takes a bit of time because there's all these many facets that adds to the calculations. So yeah, just understand that the magnitude, or how big and complex the terrain is that you bring into a simulation like that actually has an effect on how long such a simulation runs. Right, so just before we start with the Adams demonstration and training, let's just recap a few more concepts. So again, on the left-hand side, we have torque, which we said is essentially a force applied over a specific distance around a specific point. And when we apply that torque, the system will start to accelerate in a rotational manner. On the right-hand side, we have a mass and we have a force. And if we apply that force, the body will start to accelerate in a translational direction. So the concept is the same. The torque is just creating a rotational acceleration, whereas a force creates a translational acceleration. And when we apply these, we will see how the system behaves. But this is not typically what we do when we start doing a simulation. What we rather do is to apply the required motion and then measure the required torque to actually produce that motion. And that is what we've done in the simulation of Marcy over that difficult terrain. We've actually specified the speed at which the wheels should rotate, have it interact with the terrain, and then measured what the torque requirement was to obtain that motion. And this is a very interesting and important objective. And it changes how you will approach this type of simulation. It's also the best way of starting the simulation is to actually say, okay, what do we want this vehicle to do? What is the obstacle that we would like it to climb? And then measure what was required to overcome that obstacle. Okay, so I'm going to dive straight into Adams, and I want to start a new simulation to show you exactly what the user interface looks like and what the procedure is when you start building something. Okay, the first form that you get confronted with is the option to start to create a new model from scratch or to open an existing one. So if you open the one that we've provided, you'll simply use this button. Otherwise, we are going to start a new model. And then we can give this model a name. And then what is important is to decide what the direction of gravity is. And this refers to the little triad that you see in the bottom corner over here. Okay, so we've specified a model name. We've specified the direction of gravity. As I said, there's a triad here in the bottom. So currently, Y is vertically up, X is to the left, to the right, and Z points in our direction. So if you don't want to use Y or negative Y as the direction of gravity, you can change that over here, but I'll just use it as it is for the moment. And then you can choose the unit system that you want to specify your values in. And there are different ones, but the default is good enough. An important distinction, and this is especially important for the younger generation, is what folder on your computer the results and the model will be saved in. Otherwise, you may not know where to find it afterwards. So make a note of where you choose this folder, and that's where you're going to find your simulation when you need to open it next time. Then what we have in our user interface is essentially a workshop. A workshop like a garage where you can walk in and there are different tools, there are different areas, and there are different things to see. The big blue area that you see over here is the actual workshop where we will be building our model. On the left-hand side, we see a tree, which is essentially a list of everything that we have created. And at the top over here, we see a lot of toolboxes and different items that we have access to create. For instance, when we click on the Bodies tab, we have access to create boxes, we can create cylinders, we can create spheres, cones, torus, a link, or even arbitrary shapes like this. And what you can then know as well, let me just, yeah, this is very strange that it's supposed to show the keys on top of atoms and not behind it. Let me just quickly stop sharing and see if it then works. This is very strange too. For some reason, it doesn't work while the Teams meeting is up and running. So unfortunately, I can't show you the key presses. I'll have to tell you every time what key I've pressed for what. That's now unfortunate. Okay. All right. So you see that we have these wireframe views of parts, but we can also switch to a 3D or shaded view in the bottom over here. Another way we can do it is to press Shift and S on the keyboard to switch between wireframe and shaded view. You'll see in a moment why that becomes valuable. If you really want to see perspective, you can do that, but we typically don't use perspective in engineering. And then if you press R on the keyboard and you drag with your left mouse button, you will see that you can actually see the model in 3D. So the dots that you see on the screen, this is what I call my pegboard. Adams calls it the working grid. And the working grid is a helpful way for you to have literally like a pegboard, locations where you can quickly click to generate something. Like you saw me create all these entities, and I essentially clicked on these grid points. If you want the grid to be larger or smaller or have different spacings, you can set this over here under the settings work grid options. Right, so let's have a look at what happened in our model tree. In the model tree, we now see a list of parts that have been created. So for every entity that I added, an extra part appeared over here. And I want to draw your attention to the fact that the part is an entity but it also contains geometry. For instance, there we can see the torus and the part itself. So the torus is actually the graphics, while the part is the part, the entity. So if we modify, if I right click on a part and I select modify, you will see that we can modify things like the type of material that this is made of. We can define initial conditions, initial velocities. We can specify if it is a different mass, have different inertia values, are made of a different density material, or if I want to change the type of material to something like aluminium, which is lighter, you will see that these values update. We can also click on this button over here, and it will show me how much the weight and the inertia values has changed. That was when I clicked on the part. If I click on the torus itself for the geometry and I click modify, now I have access to parameters like the dimensions. 360 means that you can create uncompleted donuts like that. Not sure why you would want to do that. You can change the major radius. See that. You can change the minor radius like that. And over here, we can also change how many rings are used to represent this round donut. So if we use very few, you will see that we get a very blocky kind of design. And if we have many, we get a smoother shape like that. So that's important to understand. The same for these other entities like this cone over here. We can change the top radius, we can change the bottom radius and get different designs out of that. So I'm going to show you how we are going to use this functionality to build a little rover. But first, let me just get rid of all these bodies that I don't really need. So I'm just going to select all the parts and delete them. Ground is an entity that always exists, and that is the stationary entity or the terrain that we're going to use. So whenever we bring in a terrain like the Martian terrain, we will make sure that that geometry is assigned to ground, because that is then not taken into consideration for the calculations, and it is fixed. It doesn't move, it doesn't have mass, it's just rigid and in the way, the way we want it. Okay, I'm going to do it a little bit differently here. If I rotate the model, pressing R on the keyboard, taking my left mouse button and rotate it, we can see that gravity is pointing in the negative Y direction. If you want to change this afterwards, you don't need to start a new model. You can simply right click on the arrow, click modify, and pick any of the other directions and then apply it. Okay, Shift F is to go back to a front view, or we can go to front view by right clicking in the model area and select any of these views. So that's helpful to understand how that works. And always look at your triad over here, which shows you how the model is orientated. So what I'm going to do now is I'm going to create a box that our rover is going to move on. The box, however, in this case is not going to be fixed to ground. It's actually going to be a what do you call it? It's going to be a flat surface, but I'm going to lift it up to see how the rover deals when this thing starts to rotate. So I'm going to create a new part, and what you will see is if I simply create small boxes and larger boxes and long boxes and short boxes, they will all have an arbitrary length in the depth view of the screen. And where the other entities that I created previously was right in the middle of the pegboard or the working grid, the boxes are always on the face of this pegboard. So just understand that. And then I'm going to show you something else. Let's just get the view flat again. And that is if I decide I want my box to be 100 centimeters deep, I can just specify it over there. So what I'm doing now is I'm creating one box over there and another small one over here. And if I rotate it, you will see that they are both 100 centimeters deep or long in that direction. Okay, that was not the design that I intended for that guy. Now, the other thing that I want to do is I want to make sure that this box is not in front, but that it's halfway into the depth. And how I'm going to do that is to see that a part also has two markers in this case, well, the box part at least. The box, when I create a box, it has a center of mass and it has a marker. That marker actually dictates the origin point for the box. So if I right click on this marker and I modify its location values over here, which is X, Y, and Z, I can manipulate where this box is going to be. I'll later show you how to move things around when you don't specify coordinates. I know that we don't always like to work with actual coordinate values because it's a bit more to comprehend, but you will find later in life that it actually becomes more useful than interactively moving things around, especially when you want to work precisely. So I'm going to type in -500 millimeters. If you're unsure what your units are, you can go to settings, click on units, and you'll see that your distance values are entered in millimeters, except when a different unit is selected or specified in brackets, like in this case. So if a different unit is entered, it will interpret that unit for you, or if you don't have any units defined or specified, it will use this. Okay, so I've now modified the Z value, the out of plane value of that marker, and I'll press apply. If I rotate my model now, you will see that my box has indeed shifted into the screen. Okay, what I'm going to do now is I'm going to create the body of my rover. So let's say this rover is about, let's just check what is the distance between these pegs. So if I go to my working grid, I'll see that the spacing between pegs is 50 millimeters. So that means this box is 100 millimeters high and it is 400 millimeters long. And because I created it with the depth of 100 centimeters, it's much, much longer than it's supposed to be. So how do we fix that? We simply go to this new part. We right click on the box and we say modify. And all I have to do now is to change the coordinates or the length. Oops, my screen does weird stuff at the moment. Let me just delete this guy that I didn't intend to modify. So I'm going to modify this box. And the dimension in Z, I only want to be, let's say, 20 centimeters. Would that be okay? Let's have a look. Yeah, I think that would be fine. So that is going to be there. And let's see what happens if I run a simulation. Now, the cool thing about Adams is your model doesn't have to be complete to be able to run simulations. So what I typically do is I always run simulations as I go along and build little models to see how things are progressing, especially when you work with complex models. You want to know that something is wrong long before you finish so that you can fix it there and then. So all you have to do to simulate and see what is going to happen, how these things are going to act under gravity, is to go to the simulation tab, click on the gear, and then on the simulation form, we can decide how long we should simulate for. So I want to simulate for 2 seconds. And I want step sizes of 0.01. That gives me 100 steps per second. A step is essentially a frame. Like videos consists of frames that play after one another. If I want to see the animation, this is going to determine how many frames I'm going to have for that animation. So if I use a large step size, I won't have so many frames and it would look like maybe quite staggered, whereas 100 is quite good. Okay, so I'm just going to press play. And all we see is that both bodies that I created started to accelerate down and fall into oblivion. But I said this must be a platform. So I want to connect this platform to ground with a joint so that I can actually lift it up and have it rotate. I'll explain how this is done in a moment. So for now, I'm just going to show you how I've done it, and then we will talk through how exactly this is done. So when I press, just zoom out a little bit. When I press play now, we will see it is now rotating about the point where I added a hinge, and that guy is still dropping down. Okay, for the moment, I don't want the platform to rotate. So I will just quickly add a lock joint at that location. And what happens now is that body stands still and the other one falls. Now, the first thing you should wonder is how on earth did it fall right through? And that's quite simple. That's because we didn't tell it that it must check for contact. Contact is a very complicated analysis, and it can take a simulation very long if everything makes contact with any other thing. So by default, we don't have contact between all bodies. We only have contact between the bodies that we choose. So that helps us to have these simulations run much faster. So to set up contact, I'll go into forces and I'll select the little droplets over there. And I am simply going to use the default settings as is. All I have to do is to pick the two different boxes that needs to make contact with one another. So if I pick the first box and pick the second box, you can now see that there's going to be contact between box 2. You also see it highlighted over here. Part 3 has box 2 and part 2 has box 1. If I press OK, we see a little icon over there. And if we run the simulation now, we can see the box drops and falls down. That doesn't look too impressive, so let's lift this box up a bit. You'll see that this box also have a corner coordinate, and if I right click on any location, I'll see a list of entities behind my cursor. So for instance, if I right click over here where there's nothing, I'll see view options. But if I right click over here, I'll see the part, I'll see its box, I'll see its marker, I'll also see ground and the marker of ground as well as the joint. But if I right click over here, I only see contact. So if I modify this, I hand back to that form over there. And if I want to move this box, I will simply move its marker. Or I can use a tool that is hidden in here to actually move it. Now, this tool in itself is not the useful one to use. What I prefer using is this guy over here. Now, if you see an icon over here at the top with a little triangle, and you right click, you get access to other options. And there's many different options that relates to how you can move things. Now, the one that I like using is this one with the precision dialog box. And then all I have to do is pick the part that I want to move, pick the magnitude of the movement. So let's say we want to move it by 100 millimeters and in a positive direction in the Y direction. And there I've moved it. So that is quite useful. And now if I simulate it, I'll see the box drop a little bit higher. And you'll see it wiggle a bit over there. Okay, so this is the body of our rover. Now let's add some wheels to this rover. And I think the Tauruses are going to be quite useful in this case. Maybe that's a bit big. Let's use a little bit smaller ones. Purposefully not going to build it symmetrically so that we can look at a few other things. And I'd like to connect these to arms that will connect under the body. So let's say something like that, for instance. Okay, so the intent here is that this body or this arm must have a joint with the body over here, and there must be a joint with the wheel over here. And it is at this point that I want to highlight the fact that we don't need detailed CAD to develop a concept or a model. So if you have an idea of how you would like the suspension of your rover to work, you can very quickly generate it here. And the nice thing about this geometry is if we move any of these markers, we can easily readjust the whole model. So if I just press run now, you'll see everything just falls except for the body of the rover. The other things haven't been connected. So let's connect them. And I'm going to use the revolute joints. If I double click, I can create a few of them. And notice the text here at the bottom. Every tool that you use typically has a few steps, and this text over here will actually show you what the first step is. So in this case, it asks you or tells you select the first body. So I'll select the arm, and then the second body would be the wheel. And then it asks me for the location of the revolute joint, which would be this guy. And by default, it creates it normal to the grid. In other words, my grid that is flat over there, I now have a joint over there. Now also notice that it doesn't bother me at this stage that this wheel is going through the arm. We only consider or worry about that when we start dealing with the actual detailed CAD. For now, we just want to work with a concept. This is literally just like a sketch on a piece of paper that we want to try out. So let me create another joint between this arm and this body at this location. And let's see what happens if we press the play button now. Oh, there we see no contact between the wheel and the rover, but we can actually see that the wheel is indeed at least connected to the rover. Okay, so next step is let's create contact between this wheel and this ground. And we find that under forces. And I'm going to pick the first solid, which should be this guy, and the next solid, which will be this guy. Press apply, press the run button, and we have progress. Our system is starting to behave like it should in reality. Now we can quickly fix the rest of the system. Create joints between those parts and create contact between this body and this body as well. So now when we run, we see stuff happening. Okay, you would obviously notice that I've only done one side of the model. And the good news is we don't need to model both sides at the moment because we're still working on a concept. It's going to be double the amount of work if we want to play around with different ideas in different locations. So all I'm actually wanting is a two-dimensional simulation. I don't really care at this stage about this thing flopping about in the other directions as we saw over there. So what I would rather do is I'm going to use another type of connector, which is called a planar joint. And what this is essentially going to do is it's going to make sure that this body is locked to ground in a way that it can only slide and rotate in a specific plane. So what you will see now when I press simulate is everything stays nicely in a line. Okay, so that is just for now. Later, when we are happy with our concept, we can do the other side of the rover as well. But for now, I just want to play about a bit. Okay, so question is, we now have something with wheels and arms and a body, but it's clearly not going to support itself. So let's see how heavy is this body? I'm going to go to modify, going to click the calculate button. This guy weighs 30 kilograms. Quite important because the mass is going to determine how stiff any spring system should be that needs to carry this thing or actually keep it up in the air. These wheels obviously have mass as well, so you can have a look at that. That one only weighs 900 grams. That one will be the same and similar for these components over here. Okay. All right, so let's create a small spring damper system. I'll create a spring that attaches from this point to that point. And always check in the 3 dimensions that you are indeed applying it to where you think you're applying it. It's very easy to think you're applying it to that corner while all the way it's actually applied to that corner. So I'll always, even if I work essentially in a 2-dimensional system, I'll always check that I've done it correctly in the 3rd dimension. And let's create something similar on this side over here. All right, and of course, I want to see if that made any effect at all. Well, first thing that I can see is I've clearly connected this spring to the ground, to the pegboard instead of the body. So that's a no-no. So let's delete that. And I think the reason why that happened is because there is not a marker on that box. I can try, but I think this is not gonna. Oh, that did work. Okay. So be careful where you pick. Although I'm not 100%. Okay, no, I think it's right. Okay, cool. So I've got that sorted. You'll see me now and again click this little arrow here. This is a way to clear the list. You'll see it at the tool tip. It's clearing the selection. So anything that is selected is active, and when I click that, nothing is selected anymore. Okay, so we've got a body, we've got some wheels, we've got some arms, and we see that it just drops dead onto its belly. So clearly these springs are not stiff enough. So now we either need to go calculate what they should be. And I haven't done my homework. I'm a lazy student. So I am just going to play around a bit and see what happens if I make that 10 newtons and I make that one 10 newtons as well. So I'm basically just playing around, seeing what happens. And we can see, oh, it's almost there. So when it drops, there's some action and it looks like it can actually sustain itself. You did see that it's extremely wobbly, and that is because I didn't increase the damping coefficient. So this is a spring damper system. Now in your Mars rover, you'll have to, represent what you're going to build. So you're probably not going to have a damper system in there, but if you do, you'll want to know what this value should be. I'm just going to increase this value. Same for this guy, make it a bit more stable, and let's see. Okay, I think that can actually work. Maybe a bit under stiff, so maybe we must just increase the stiffness a little bit. Let's say by 2 newtons. And let's see what that does. Not much different, but it's doable. And because we have that, just switch this on, because of this planar joint, Sorry, this was not jumping. Because of this planar joint, everything stays in line. You'll see if I deactivate this joint, you'll see the system will fall over. Okay. Because we don't have wheels for the other side. But because I'm still experimenting, I'm activating that joint. Just want to make sure I activate the right one, so that I only have half of the vehicle to worry about. Okay. Okay, now let's see. Let's start to add a motion to one of the wheels. And one of the ways we can do that, pardon me, is to select one of the joints, like this revolute over here, and specify a value for the motion. So in this case, I am going to apply a motion. Now by default, it is free to rotate, but I'm going to fix it, and I'm going to say, okay, I want this to rotate by 300 degrees. That's what the D stands for. Otherwise, it accepts it as a radians. So if you want to specify it as a degree, you have to add a D. So I want this to rotate by 300 degrees every second. You'll see that we multiply by time. Adams understands time. So this means at time 0, the displacement, the rotation will be 0 because we multiply by 0. At time 1, when time is 1 second, the rotation would have been 360 degrees. And by 2 seconds, it would have been twice that. So let's apply that motion and see how this affects our system. Okay, so the interesting thing is we clearly see the wheel is rotating, right? But it doesn't look like it's taking our rover anymore. So what is wrong? Well, what is wrong is that firstly, default contact does not have any friction. And friction is needed for a wheel to get a grip. So we have to switch on friction. And I'm just going to use Coulomb friction. And for the moment, I'm just going to leave all the default values as is to make it easier. Okay, we'll fix the default values later and you'll see why. So now I've got some friction and we can see that this guy starts to move. But look at the front wheel. The front wheel is actually skidding along. And that's for the exact same reason. Its friction also isn't activated. So I also have to modify its contact and switch on friction. And if we simulate it now, we'll see this one is driving and that one is just being pushed ahead. Let's see what happens if I let it go for another half a second. Yep, there we go, across the side. What you'll also see is those arms go right through this body. Again, because we didn't specify contact, but it's not necessary. The contact we have specified is sufficient for our purposes. Okay, but I want a 4x4. So let's add the same motion to the other joint. Also going to impose a motion. And I'm also going to specify 360 degrees times time. And let's see what's happening here. Now it's running the other direction. What the hell is going on? Well, I know, but I also know that you don't know. So let's have a look in wireframe. This is why wireframe is actually quite nice to look at. When we press the play button, I see this wheel is driving this way, this one is driving that way. And the reason for that is the second joint was defined the other way around. So all that means is we must just specify its motion in a different direction. So we can just do that by adding a minus in front of the formula. And when we simulate now, if I can just get my model under control. We simulate it now, we see both wheels are driving in the same direction. Now remember what I said in the last slide, that we can apply a rotational motion or a torque. Now we've applied the motion so that we can measure the torque, and this is actually what we're after. So we want to know, in this particular case, how big the motor was to have this vehicle move in that specific direction. So another way of looking at results is to go to the Results tab. If we just click on the film, we'll just see the animation. Most of the time playing faster, because previously it was actually busy calculating the dynamics of the system, whereas now it's just replaying the results for us. Or I can go into the post process, and the post process is where I can see much more detail. This is where I have lists of everything and quantities of everything. Torques, displacements, rotations, velocities, accelerations, as long as we know what is what. And this is where naming your components starts to become useful. So let's just do that. I am going to define this as the front of my vehicle, and I'm going to change this joint's name to be front wheel. Just be aware, you're not allowed to use spaces. This box will turn yellow, and that means there's an error. And that error is typically because you've used a character that's not allowed and a space is not allowed. So we'll just say that is front wheel. And this joint I will rename to be the back or the rear wheel. Okay. So when we go in here, I can see, there is the joints that I'm interested in. So if I want to know what's the torque on that wheel, as well as the torque on the other wheel, I can simply select both of them, select the torque, select the direction, which I just use. It's easiest to just simply use the magnitude, and I get an idea of how much torque is needed. So we can see we only need blips of torque. We don't need a constant torque. Don't think that because there's one single spike at a specific value that you now need a motor that can supply that amount of torque all the way. That is definitely going to give you a big surprise, because in reality we just need to give it a little bit of torque, bits and bits of torque to get that exact motion. So if we're going to change the model to have torque applied instead of motions, it's going to be quite unpredictable. And what you will typically see is that it's going to start accelerate. All right. But before we start playing with that, I want to do something else. I actually want to deactivate this lock joint. Obviously, if I press the play button now, we will see everything falling dramatically. I want to add a statement to this joint. I want it to rotate by 10 degrees every second. Now I just need to check the direction. Yep, that was too fast and in the wrong direction. So let's rather make that. Oh, that was because I didn't add a D. So there's a big difference between 10 times time and 10D times time. That is why that didn't go so well, and it's going in the wrong direction. So let's just put a minus in there. So what we see now is our rover traveling uphill and then sliding back. Okay, so this gives us an idea of how steep an incline our rover will be able to navigate. And when it gets at that point, that's where it starts to slide back. We see time is at 2.1 seconds. So if we multiply 2.1 by 10 degrees, we see that's about 21 degrees where it starts to slide. Now, one of the reasons it's sliding at that point is primarily because of the friction. And if you don't know what the friction should be, there are lots and lots of examples of typical values. But what you can also do is, with this form open, press F1 on your keyboard, and that opens the help files at the relevant topic. So because I had the modify contact form open, when I pressed F1, it opened up my help files at F1. So the tip that I want to give you, if you don't know what friction value you should be using, you can click over here on contacts, and then there's a link here to material contact properties table. And this is just some, I would say, good guess values. It's something that can be extensively researched for your specifications, but the friction values are always between pairs of materials. So you will see values from 0.7, 0.23, 0.1, but on the left-hand side, you will always see two different materials. You'll never see a static or a dynamic friction value just for steel. It will always be either steel on steel or steel on something else, or in this case, plastic on steel, or a nylon on steel, or aluminium, etc., etc. Because friction is a function of the two materials that are in contact. So I'm looking at a rubber. I'm going to have rubber wheels on my rover. If it's going to be aluminium wheels, we will have to look at some other values. But in my case, I'm definitely going to use rubber. So I can see that rubber has a static friction coefficient of 0.8 and a dynamic friction coefficient of 0.76. Now, for those of you in school who haven't worked with that or don't understand what this is all about, this is something that you will learn at varsity, how friction works and why the static coefficient is always a bit higher than the dynamic coefficient. It actually makes for a nice demo if you want to show a student why old cars don't have disc brakes at the back, but have drum brakes at the back and disc brakes at the front. And it actually has to do with this phenomena that your static coefficient is higher than the dynamic coefficient. So let's just leave me for now and just make sure that this is the same for these guys. Now, what we must also remember, the friction value that I've chosen is actually very high because it is rubber on a dry surface. If we're talking about a sandy terrain, that's going to be, again, much lower. Okay. So it's not a simple task to know exactly what the friction coefficients are. There are tests that can be done. It's actually a whole study field on its own at varsity, and many professors have earned their degrees studying those things. So it takes a bit of experimentation to know what the exact values are. But let's have a look at what the effect is on our rover. Now we see our rover is actually driving quite well. Let's have a look. Let's drive it for another half a second. Okay, there it starts to slide down. But it actually gets up much further at a much higher angle than it did before. Okay, so obviously we need some friction. And if we going into the post processor and refresh these values, we will see that the torque requirements have changed as well. So now I want to change the behavior a bit around. Instead of defining the motion, I'm going to define the torque. And looking at these value, a torque of, well, definitely not as high as 10, not even as high as 5, something as low as 1 Newton millimeter should be sufficient. So what I'm going to do is I'm going to right click on the green arrow, which is the motion, and I'm going to deactivate the motion so that we don't have that defined anymore. And if we simulate this, this is just going to roll down the hill. You can see that by checking the wireframe. Yeah, okay. All right, so now I want to apply a torque. And I'm going to apply a two-body torque. This is important. A one-body torque and a body fixed torque, those are not really valid. We have to work in our case with two bodies because we want, in this case, a torque of, let's say, 1 Newton per millimeter between specific bodies. So we want it between this part and that part at that location. And for the second point, this is a trick for some reason. You have to select it in the right click menu over there. Now let's see if the torque is in the correct direction. Not sure. Not sure if that torque is indeed. Let's make the torque higher. I'm just going to make it much higher. See what the direction of the torque is. Yeah, difficult to see. I think it's in the right direction, but let's increase that value even further. Very difficult to see, actually. Because you want to make sure that the torque is actually in the correct direction. And currently, I'm not sure I've done this correctly. Between part 4 and part 6, so that's at least right. I'm not sure why I don't see that wheel spinning by now. It should have. Yeah, now we see it. Okay, now it's clear. Just want to see, maybe I read the graph wrong. So let's just go back to the graph and see if there was any funny units. So it was Newton millimeter, so that should not have been needed to be that high. I'm going to switch it back to, let's say, 5. Maybe what I should do is just keep this level for the moment. So let's just deactivate the motion by multiplying it by 0 and see what happens. Not much. Looks like something wants to happen there. Clearly not a high value. Oh, it's actually rotating the wrong way. I thought as much. Okay, so we actually want to apply that in the other direction. Really, that is not high enough. There we see something happening. Okay, now I'm going to apply a torque on the other one as well. Again, make sure that it's a 2 bodies option. I'm going to apply a torque of 500 between that guy and that guy at that location, that marker. So let's just deactivate this guy for the moment and see what happens. Okay, so that one is rotating the other way around. So I'm just going to make that a negative as well to make sure that it's rotating the right way. And now I can activate the other one so that we actually have a 2x2 car, 2x2 rover. Okay, great. And if we go back to our joint and modify its motion so that it starts to lift again, we'll see that it battles to get up the hill. And if we check something, Shift F, okay. Okay, so it's going there. So if we go to the results, it's still showing the old results. That's not valid anymore. I'm just going to create a new page. And I'm going to split the view so that we can put the animation in on one side and the results on the other side. So this side, I need my 2 motions. Sorry, I'm looking for where's my forces? Let me just go back and give them proper names. So this torque, give this one a name. Okay, so if we go back to our results, did not update with the, there we go. There's the front torque and the rear torque. So you can see both were simply 500 all the time. It was a constant torque that was applied. But if we're going to look at the angular velocity, you'll see that it looks very different again. So the Z value is the angle of rotation. So even though it looked like a smooth animation in the beginning, you can see the wheels started to spin and then it started to reverse as it went downhill. So the torque was not enough to pull it through. Okay, now I want to show you something that's also going to be very useful, and that is how to use variables. Because what you've seen up to now is me having to change two values every time. So if I wanted to change the values of both springs, I had to go to each one individually and manually change them. And the same for the two motions, or at least the two torques. So this torque is minus 500, and this torque is minus 500 as well. But now if I want to play around with even more values, I don't want to modify it in two places every time. So what I'm going to do instead is to create a design variable. And this I do in the design exploration stage, where I'm going to create a design variable for the torque. And I am going to use a unit of torque, or let's just use, yeah, torque is fine. I can find it in the list, torque. I am not going to use the negative. I'm going to leave the negative in the equation, but I'm going to copy this name of this design variable. The design variable is now created and it's listed over here. And then I'm going to change my formulas. Not that formula, this guy's formula, the torque over here. And I'm going to say that has to be negative the torque value. And the same for this guy, negative the torque value. So if I run the simulation now, the results will still be exactly the same because I didn't change the quantity. But now I only have to change the torque value over here. So if I make this value 2000, we will now see the 2000 being applied to both sides simultaneously. So that's quite convenient, so that I don't have to model each or change each one's value. So even more so if you're going to model the right-hand side of the rover, when you are done and you want to make changes, you definitely don't want to do that for all four individually, so it's much easier to just do it in one place. Okay, now I'm going to do something interesting. I am going to put in a little obstacle and see if the rover can actually get over the obstacle. And before we do, I'm just going to deactivate this again by multiplying that by 0. So this is what it's going to look like. And I am going to add a little box again. But this time around, I'm not going to create a new part. I'm going to create the box to an existing part. And you will see that over here at the bottom in the text, it says select the body. So I'm selecting this body. And now I am creating a little box. And what's happened now is that this part 2, let's rename it to platform, that we know what this is. Platform. We'll see that platform now has 2 boxes. Okay. And let's see what happens when we simulate. Oh, that's interesting. Our wheels go right through the box. And why is that? Well, quite simply, because we haven't told our contact to also consider the new box that we have that we wanted to make contact to. So I'll just add the new box as well. And you will see that both boxes are now listed over here. And I'll make the same change for the rear contact as well. So now when we ride, it's going to bump into the first obstacle. And as you can see, the obstacle is too big and we can't get over it. Okay, now we saw that we've already increased the friction to quite a high value, so it's very unlikely that we will be able to increase the friction enough. So we have two choices. We can either decide that's a day and we'll never be able to overcome an obstacle of that, or we can say, well, let's just create bigger wheels. So let's do that instead. Let's change the size of our wheels and see if that doesn't help us to get over that obstacle. So I'm increasing the major radius to 50 millimeters, gives us 100 millimeter diameter. And let's see what happens now. And we see, okay, it's bigger and it's definitely not getting us up there. You can see that that friction force is not high enough to lift our vehicle. I'm also a bit worried about these springs that are so flexible. So let's change them. Let me create another design variable. Spring stiffness. Make that stiffness. Where are you? There we go. I think the existing value was 12 or 15, 12, yeah. So let's make the new one 15 or even 20. Let's see what that does. And we copy that name, come in here and specify that it's simply the name. We don't need to use the units because we've already specified it as a stiffness. And I'm going to do the same for this guy over here. So now again, we only have a single value that we need to change. So let's see if that makes a difference. Okay, it's definitely not getting over there, so let's make the wheels even larger. Taurus, modify. Let's make that a 75. That's much better. And let's see what happens now. Yeah, I think our motors are not strong enough to get over that ramp. So bigger wheels isn't helping much. We need to increase the torque. And I forgot we have a value over here. So let's double the torque. Ah, there we go. Nice and easy. Might even get away with smaller wheel radiuses. So let's even create a variable for that. Wheel radius. I'm going to give it unit of length. Currently it's at 170, I think. 170, oh, just 75. Yeah, 75. So I'm going to reduce that back to a 50. Copy this name over here and change this Taurus major radius to the wheel radius, and the same for this guy. Oh, okay. That one, 45. Nope. Our wheels, even though the torque is now higher, the wheels are too small. So let's just change that a bit bigger. Let's make it a 60. Let's see what that does. Nope, not big enough. Let's make it a 70. Yeah, that works. Cool. Let's see if we can add another obstacle. This time around. Ooh, must not forget, I don't want a new color. This is a new part. I don't want that. I want to add it to an existing part. This guy, and I'm going to do that. So let's see if we will get over that obstacle. Again, forgot. This new box also needs to be added to the contact. I'll go back into the contact and pick the new box. So now we have 3 boxes in the same part that we also need to add over here. Just not enough. So like that, we can play for as long as we like to see if we can get this right and what is the correct combination of values that we will need to pass this obstacle. Excellent. Okay, so I want to open up the opportunity for you guys to ask questions. I hope this has given you a good start or starting point from where to how to set up a model from the basics from the beginning.
Paul?
Yes.
Can I maybe just do a recommendation and maybe show them how to rename the parts so you don't sit with part 1, part 2, part 3, part 4. Just to tidy up your model a bit.
Yeah. So I've done that for the platform already, like the platform over there. But for this guy, I did not. So this one would be beneficial to rename to front wheel. That definitely helps a lot to know what's going on. So now it's easier to manage the different things over here. That guy is the body.
Okay, Paul, while you're in there, Caitlin asked in the chat, if we run into any major issues when using the software, is there anyone we can contact for support?
Very, very important question. And thank you for reminding me. There's a link in here that I'm going to paste in the chat. This is a link to a LinkedIn group. So I suggest you create yourself a LinkedIn profile. And this group was specifically set up for you to ask questions, and you can even assist one another over here. LinkedIn, if you don't know, is a professional social media network where professionals connect. And this is not where we share videos or pictures of our dinner, but we will share knowledge, we will share events that we've attended. And in general, it's a professional network where people showcase their expertise. So it's very good for you as a student to have a LinkedIn profile, start following professional companies that you want to know more of, or that you're interested in to work for one day. If you want to move into a specific industry, or if you have a specific interest in a specific industry, go and follow those companies in those industries. It's a very valuable place to start building up a portfolio for yourself. So that's why we created this LinkedIn group. We hope you will also follow us.
Paul?
Yes.
There's 2 questions basically asking the same thing. They want to know if you've got a CAD package like Onshape or SolidWorks, how do you get your designs into Atoms?
Okay, yes, that's a very good one. Sorry, I'm just running out of juice, so I just need to change set. Okay. Okay, let me quickly show you how that works. That's actually a very important point. So I don't have an example handy at the moment, but to give you an idea, you will go to File and then Import. And this is where you have the option to import many different types of files for many different types of purposes, but also your CAD files. So we see some known CAD products like ProE, SolidWorks, Inventor, CATIA, etc. The alternative is to simply use a general file like step. So you will take the CAD that you have in your CAD package, export it as a step file, and then select the step function, a step file option over here to import. You will then browse to your file, which I don't have an example now ready. And then you need to decide if that geometry represents a single part or multiple parts. If it is geometry for multiple parts, you need to import those into the model. What that then does is each piece of geometry that you import, a single part will be created from it. Now, it's important to know that, like for instance, in this example, there's a platform that consists of 3 boxes. Maybe let's do it this way. Let me export this as a step file and then re-import it so that I can show you the different options. So I am going to go to File, Export. I'm going to choose the format as step. I am going to export it as sample geometry. And this is where that working folder that you selected when you created the model in the first place is important, because the file is going to exist there. And if you can't remember where that folder is, you will now have to check here. So File, select Directory. This is the location. Now, I don't want that file to lie in my user directory. So I am rather going to choose a folder where I typically save all my files. So I'm going to go to my training folder. I'm going to create a Cars4mars folder. And this is the folder that I'm going to use where I'm going to export everything. So in my case, I only want to export the geometry of the platform. I'm not going to apply any transformations to it. That's all that I'm going to do. Okay, so what it's done now is it has exported the geometry to that location. Let me just quickly find that location. to show you what the file looks like. Just give me a second. I'm working on the other screen at the moment. Okay, cool. So here is the folder, and here is the geometry that I've exported just now. Okay, so let's hide this part for the moment and import. I think I can close these guys. Import the geometry. And I'm going to select the one that I've just exported. And this time around, I am, okay, let's start and actually import it back onto the same part. So what we should see now is additional boxes appearing here, or at least geometry. So let's do that. Just want to check the other default settings. Everything should be fine. Okay, so it says the objects have been consolidated to one shell, and that is what I'm seeing here. The part's not currently visible because I've hidden the part and not the boxes. So if I want to hide the boxes, I'll see the shell. So the shell could be a different color. It could be brown. Oops, that won't work. All right. Whereas those guys are blue. Okay, so we actually see, oh, strange. Oh, yeah, I see. I never shifted those two boxes. I should have done that. We can quickly correct that. Should have been minus 500. Same for that mark over there. The imported geometry now I won't be able to modify anymore because it's now a single shell. Because I've exported it in that shape, it's just going to be stuck like that. That's a single entity that I cannot modify, but the original boxes are still there. So that's exactly how you can import geometry that you already have to bring in and apply. Now, what the benefit of imported geometry is that it will look nicer, because we typically design stuff that looks nice, and because it will probably have a more accurate shape, you will be able to calculate a more accurate mass and volume. And the other thing is geometry is also used for contact. So when these two parts collide, the amount of overlap between the geometries is what is used to calculate the size of the force that it needs to develop. And if you have a more accurate geometry for this terrain, for instance, the interaction would be more realistic, and the same over here. So if this was supposed to be a hollow box, obviously it won't weigh 30 kilograms anymore. It will probably only weigh 500 grams or something like that. So when you have actual geometry, at least you have a better representation of the mass as well as the distribution of mass, because the other values, don't know if you saw this or are intrigued by this, the other important values that you see are these three, and these values are critically determined by the shape of the geometry and the where it is thick and where it is thin. These values dictate how fast or slow a body will rotate when you apply torque to it, whereas force and mass determines the linear acceleration. And then, as I said, if you have more realistic geometry, that also helps with contact. But I think the important thing that I wanted to show here is that we don't need we don't need the realistic geometry just to play around with a concept. Maybe what I should do, oh, this is actually this is actually something useful. Let's make a note of this as well. If I want to play around with different locations for the joints, it's much easier to do this in Adams than in a CAD package, because in a CAD package, you will have to recreate the geometry accordingly. What I'll do in Adams is I will create points that I can then move. And what I will do is I will add these points onto Gail. You said this function works in your version of Adams. Why is it not working on my side? Is it because I'm sharing my screen? These drop-down boxes doesn't work.
I think there is some couple of issues that come with that, because
that is quite strange, and it's only for the points. So I can create a point, but I don't have those options to create near, which is now a bit of a pity. Sorry guys, it's something on my computer and I don't know. I thought formatting everything would have solved it, but this clearly doesn't. So when you create geometry points, you can add it to ground, but what I want you to then do is to create the attach near option. What that does is it allows you to create or to replace everything at that location to be relative to this point. Because if I don't do that, there's a lot of markers in this location that are not linked to that point, unfortunately. And I don't really want to modify all the different markers and the locations, because you can see these are all static values. But if you create a point and you say attach near, when you create it over here, all the markers at this location will then reference that point. And what that gives you the ability to do is to modify the location over here. So let's say make that -150. And then not only the point moves, but all those attachment points move as well. And that's actually very favorable for something else. And that is that we have the ability to play around with design of exploration, where, where we can specify, I must just remember which option that is. Nope. For instance, you can set up goals and targets and constraints, and then have the software find optimal values for you. So for instance, if it was really important to get the combination of torque and wheel radius that fits nicely with this thing getting over this bump at a certain speed, that would have been very difficult to manually find an answer for. What you could do is to say, okay, I'm going to measure the torque, and I'm going to modify the torque, and I'm going to modify the radius of the wheel, and I'm going to measure the body's velocity in this direction. And then I'm going to set a goal that it has to pass this point at a certain speed by changing the torque and wheel radius values. So that would be one example where it becomes valuable. Another would be if we put a design variable for a location, we could then move things around. For instance, what if we don't attach the spring at the top over here, but attach it at the bottom? or a bit lower. Changes everything. But if we specify variables for that, then it becomes much easier to do these design of experiments and let the software actually assist us in finding optimal values. Okay, so I hope you understand how to bring in geometry. Oh, the other thing that I wanted to mention is, and let's see how that works. I'm just going to delete that shell. If you import existing geometry like that one, but you don't select to import it to a part, you import it to the model, then the various bodies will be, different parts will be created. I'm not sure if this specific step file will be set up like that, but let's test it. So what you also didn't maybe realize is you can have models within a model. So here, this was the Adams model, but when we say save, you don't really save the model, you save the database. And you can actually have different models inside this database. So when we select to import the geometry to a model, we can actually select different models in the same database. But I only have this one model, so this is the one that I'm going to pick. And let's import this now and see what happens. It says it successfully imported the body. But now you'll see I have 3 different parts. So when I imported the geometry into a single part, like this, and I specified it has to import that to the platform, the whole piece of geometry was attached to the platform. But when I imported it to the model, each body came in as became a new part. So that's very important to understand about Adams. If you're going to import a complete rover model, you probably would want to import it into the model so that each body becomes a part. But now I need to warn you of something else. This is the free student version. The commercial product costs about 800,000 Rand, and I'm not kidding. This is proper industrial level software. So the student versions are limited. It's purely there for learning, and it limits you to 20 parts. Now, at the moment, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 parts. So I'm still halfway to the limit. But if you now have a CAD file that consists of 20 pieces just for the body, and you're going to import it, it's going to want to create 20 parts for each one of the bodies that's representing the body. So be careful, don't waste parts on bodies that are connected and doesn't move relative to one another. For instance, this ground for now. Here I have now 3 parts that are representing the work of a single part. So it's better to have import all the solids per part. So if you have, like in this case, multiple solids that represents a single part, export them separately as a file and import them onto the part so that you have as few parts as possible and don't waste the 20 parts that you have access to in the student version. So in general, you definitely don't need many parts. If we have a look at our rover, the one that I've showed you in this video, it didn't have as many parts, But if I were to break it down into, if I look at the CAD file actually consisted of many parts. But because I didn't let all the panels move relative to one another, and they didn't move relative to the body, I just brought them in as a single part. In the CAD file, this consists of many different parts because there's 4 solar panels, each one of them is a part. Then there's all little bits and bobs on the body. Each one of those are a little part in the CAD assembly. So the trick here is to select all the bodies that will represent a single moving object and export that as one CAD file and import it into Adams to a single part. Because you don't want to waste your capacity on parts that need to be fixed together. So even though you may have 20 bodies representing the body of the rover, you literally only need one part. So then you rather want all these bodies inside the single part. I hope that is clear and that everybody understands that. All right, do we have any further questions? If not now, please ask your questions in the LinkedIn group. As I've shared, you're more than welcome to share your progress over there. The group itself it's a public group, but not everybody on LinkedIn will see it. So it's only for us. So you're more than welcome to share there how you are progressing or what you're struggling with, and we will gladly help. But the idea is to help everybody, not just yourself. I doubt. Oh, the other thing. Okay, this almost forgot to mention, and that was the training files that was provided to you alongside the software. So this tutorial booklet, as you saw, is quite comprehensive. 352 pages. And I think, if I remember correctly, more than 50 or about, actually 50 examples of problems. And these take you step by step through the different examples. So for instance, if we look at example 2, that is the inclined plane on page 14. That is a tutorial similar to what I've done, where there's a ramp and a crate on top of it, and you specify the friction. And the steps are very clear, exactly what to click, where to click, how to change the pegboard, that I like to call it, or the working grid. They teach you how to use the user interface. So they don't only go through the specific example, but they also teach you how to do basic things in Adam. So it's actually worthwhile to work through those examples from the beginning. And as you'll notice, you can end up with much more comprehensive or advanced examples, like having a control toolkit in the simulation. So the idea with that is that if you are designing or programming your control system, that you actually test it on the body or the bodies of the actual model. So that Adams can calculate the physics, how will the body react to the inputs, to the accelerations, to the forces, and those accelerations or new positions are then fed back into your control system, basically simulating a sensor, and you can test how your system then reacts and adjusts for those input values. So you can build really, really advanced things with Adams. There's literally no limit. The only limitation you're going to have with the student version is the limit of 20 parts, but apart from that, you can do almost anything. I mentioned the optimization, so this is a useful example as well to learn more about that. But to learn about the user interface in a bit more detail, I would advise you to work through these examples. As you move on, you learn more and more to the point where you eventually have flexible bodies in the system as well. Right, are there any other geometry? Geometry. Any other questions? How do we generate the rocky terrain as shown in the rover simulation? So in the on that website that I gave you the link, if you go to simtech.wetransfer.com and you download the file that we've shared, you will actually find an example model. I must now just check myself where exactly that is. So in that bundle that we've shared, I don't see it now. You should have received a bin file. It's called a bin file. So Adam saves its database as a bin. And if you open that bin file, that already has the rocky Martian terrain in there. Then you don't need to do that from scratch. Just be aware that that file is large, so it does affect how long things take. So it might seem that the software is slow. It's just because the file is quite big. But yeah, if you have the software, you should have that model as well. The model that I've given you has the terrain, and all it has in there is a ball that's in the air. So should you simulate it, you'll see the ball drop and roll off the terrain into the oblivion. So that is a nice place to start with your model, and then you'll be able to do something similar than like what we have over here, where you have this big terrain where you can have your model drive on. And as I said, my recommendation is always start with a motion so that you can kind of get, define what you want to do with your car. So this one, we used step functions to change the rotational speed between left and right. So this little rover of ours doesn't have a steering system. Of course, you can build in a steering system, but this one doesn't have a steering system. It just uses the different rotation speeds between left and right to rotate. Not something that you want to do with a car driving on tar, but on gravel, that's fine. We purposefully built this little rover with only 4 wheels. We saw that most of you guys copied the classic rover. This is just to emphasize, rover can take on any shape or form. It doesn't have to be like the examples you see on Mars, actually. That does not mean that those are the best or the only way to model a rover. Be creative, try out your own things. But you don't, the point we want to make is that you don't have to build it before you know whether or not it works. You can literally start with something very simple like this and modify it much quicker than you can an actual model. As you saw, this meeting has been recorded, so we will make the recording available at some point, and then we will share it on the LinkedIn group as well. Okay, Tanishq Sharma's asking, I was trying TAT1 and while renaming my part, I got this error message, no object named falling was found. Okay, let's have a look at that. I assume you are referring to the training file, this book that I have open here somewhere. Let me just get back to it. Where did I open it? So that one is the falling rock, page 8. So I think what's happened is you just had to rename it and you probably selected it under a different name. Let's have a look. So I think this is a mistake. I think you stumbled upon a typing error in this document. This should not have been dot falling dot stone. It should have been dot falling underscore stone. When I go down here, I actually see the component was called falling underscore stone. So it looks like a typo in the document on the specific space. Just go through. But yeah, that's typically what I think what's happened. Yeah. Oh, yeah. Okay, I know what is happening here. So it looks like, okay, they've meant to save the model. Okay, so the model name is falling underscore stone, right? And I think what they meant was to change the part name also to falling stone. So what that meant was it should have been dot falling underscore stone dot falling underscore stone. Because in Adams, you typically, as you saw here, if I rename this part, you typically see the name of the model and the name of the part, even though you only want to rename the part. So this is maybe an important distinction. If we go to the database navigator, you'll see that there's a little plus, and then in this case, the model name. The model name is in quotes because I used spaces. Spaces are frowned upon, but I like to test it out because I know everybody normally use spaces. And then under the model, we see the different parts. It's the same as over here. And the naming convention is actually showing that hierarchy. So the first bit is the part, the model, sorry. And then you see a point or a dot, and then it's the part name. So when we rename a part and it shows the model, we shouldn't rename everything. We should only rename what comes after that point. Otherwise, it's not going to work. So this is where we have to make the change. I can't come in here and say rover body. Okay, sorry, I was wrong. I could actually do it. It assumed that I meant that as well. Okay, so it's fine if it shows it to just remove it. Let's just go back to that document and see if that isn't what was happening here. Okay, yeah, so they actually renamed the part only. They didn't include the model name. So that is actually fine. Sorry, I thought it was just always a habit of mine just to do it separately. But I think the big mistake comes in here, that this should have been an underscore. If it would allow me to change this. No, I'll save it like that. All right, so I hope that clears up your problem. Glad you asked, otherwise we wouldn't have picked that up. Any more questions? Okay, if there's no more questions, I'm going to call this a day, and thank you for joining us, and please reach out to us on LinkedIn and use this group to ask your technical questions so that we can assist you. And good luck to everybody. Really looking forward to what you're going to produce.